Alright, hello class. Here's our part 2 of related rates, and we're just going to do some more examples just to hopefully help us get to terms with what we're doing here. Alright, so I wanted to start with a bit of an explanation of radians. I realized that I probably didn't explain it very well in the previous video, and that assumption that you may have seen it in your trig class may also not hold much water. Radians are dimensionless units mainly because the way radians are established is it takes the arc that is made by the angle itself, which we'll call S, and it compares it to the radius of the circle that it's in. Alright, so if you always think of an angle sitting inside of a circle, theta in radians is essentially the arc length divided by the radius of the circle. Okay, so whatever the units of S are will match whatever the units of R is. So if you think about the full circle, right, this full circle, and we have, say, radius R, and the value S is going to be the full circumference if we do the full circle. Okay, so we know that that will be, let me write it as the circumference, which is 2 pi R. So theta is going to be 2 pi R divided by R, which is 2 pi radians. So that does line up with what we expect. Okay, if we instead, right, check out a 90-degree angle inside of a circle with radius R, well, we know that this arc here is basically going to be 1/4 of the circumference, because this is 1/4 of that circle. So it'll be 1/4 times 2 pi R, right, which is going to be pi halves times R. So when we try to measure this angle theta, okay, it's S over R, which will be pi halves R over R, which comes out to be pi halves radians, right? So that hopefully aligns with what we know about, say, a 90-degree angle in radians, which is pi over 2. Okay, now the important part here is that, again, these units are the same. So if S is in meters and R is in meters, then theta is S meters over R meters. The meters cancel, and we have S over R radians, right? So whenever the units cancel like that, we end up with radians. Okay, so that's what I meant when I was saying that radians are dimensionless. It's because the way radians are built, it's basically a comparison of an arc length to a radius, that cancels out, but just by definition cancels out the units, or at least the spatial units, and that's what brings it down to just an idea of rotating around a point. Alright, so hopefully that sort of clears that up a bit. Alright, so this is a good enough segue to move into another trig-based related rates problem. So we have a lighthouse, let's say, which is 500 meters off a straight shore, and the focus beam of its light revolves at a constant rate of 4 RPM. So I have this set up going this way. Okay, so let's say that the lighthouse is revolving this way. Now I haven't written such that technically this is a negative angle, but I'm going to just assume I've drawn it backwards and that this is a positive angle. So here's our theta, and so what we're told is that d theta dt is 4 RPM. That means it makes a full rotation 4 times each minute. Okay, now while that is happening, the light is moving along the shore. Okay, and so what we want to know is we have this point Q, which is 200 meters away from the sort of parallel distance or perpendicular distance to the lighthouse. So we want to know what is the speed of the beam along the shore when it strikes this point. Right? So we have this beam of light revolving from this point, but the end of the beam is hitting the shore, and we want to know how fast it's traveling when it hits this point Q. Alright, so to show on a graph here, if this L is the lighthouse, I'm not showing the full revolution, just the part that we're sort of concerned with. It's coming along here and then hitting Q and moving through. But as we can see, even if this moves at sort of a constant rate, this will be having a varying rate as time goes on. So what we want to know is basically the speed of B here right when we hit Q. So right at this moment. Okay. So let's set up the problem, see what we can do. Okay, so first I want to know what it is that's changing over time. Well, this length right here is not. However, this length that is made by the beam of light, right, this distance here does change. So we could call this, let's say, B for the length that the beam makes from this position of the lighthouse. Okay. And theta is changing over time. We know theta is 4 RPMs. Okay. Now, what we want to know is basically what is dB dt, okay, when B is equal to 200 meters, right? The second B hits Q, right, that length of 200 meters, we want to know what its rate of change is in this direction. Again, I'm assuming everything's positive here. I did sort of draw it backwards, but that's basically because in the book they sort of draw it backwards. In general, you know, we could make it negative and negative, but in a situation like this, we don't really have to. Where we would really need to is if it's going to make a difference, right? If one quantity is decreasing while the other one's increasing, okay? Or if one, or vice versa, here both are increasing when we're looking at it. So it's not really going to matter that much. But now I want to find a formula, right, that basically relates the angle theta, its opposite side B, and its adjacent side 500. Okay, so once again, and this is pretty common, we can use tangent of theta, because tangent of theta is going to be the side opposite over the side adjacent. And notice we can actually put in the 500 here because this length right here stays constant, thankfully. Okay, and so now we can differentiate both sides, or we can move the 500 over, but I'm just going to go ahead and differentiate both sides. Okay, so a derivative of tangent theta with respect to t is equal to the derivative of b over 500 with respect to t. Right, so this will be secant squared theta times d theta dt. Okay, and then derivative of b over 500, well, we can move the 1 over 500 outside. That's just a constant, and this will be dB dt. All right, so here is the formula that relates these two quantities. All right, so this is what we're trying to find, this dB dt. Everything else we have or we can find, right? We have d theta dt. d theta dt is 4 RPM. Now, we're going to need to change that to radians per minute. Okay, so we will need to convert that to radians per minute. Mainly so we're not worried that much about units being introduced. Okay, and then we need to find secant, right? So we can find secant from the fact that we're really looking at a 500 by 200 triangle, and we can find the hypotenuse using the Pythagorean theorem, right? H squared will be 500 squared plus 200 squared, right? And so we can find secant through that, right? So H is going to be the square root of 500 squared plus 200 squared, right, which comes out to be about 538.52. Okay, so that means that secant of theta, well, secant of theta is hypotenuse over adjacent, since it's 1 over cosine. So it will be the hypotenuse, 538.52, over this side adjacent. So that comes out to be about 1.077. Okay, so now we have just about everything we need. So I'm not doing it here. For rotations per minute, right? Rotations per minute. If we want to get this to be radians per minute, well, I want radians on the top and I want the rotations canceled. So for every one rotation, that's 2 pi radians, right? Because every full rotation is 2 pi radians. So the rotations will cancel, and this is going to be 8 pi radians per minute. Okay, so we can put that in as our d theta dt. All right, so we have everything we need now, hopefully, to plug and chug and get what we need. All right, so let's break this off a little bit. So secant squared, well, that's going to be 1.077 all squared. Okay, then it will be 8 pi radians per minute. Now note, this is unitless because this is meters over meters. So this is unitless, okay? And then we'll have 1 over 500 dB dt. So this is what we're trying to solve for. So we'll just move that 500 over, okay, to get 500 times 1.077 squared, 8 pi radians per minute, okay, is equal to dB by dt. All right, now you might wonder, like, what happens to all of our, what happens to our units, right? So here, B is in meters, this 500 is in meters, okay? This dB is in meters per minute. This 1 over 500 is simply in meters, okay? That 1 is not also in meters. So this 500 is in meters. This is unitless. This is technically unitless because it's radians, okay? So when it's all said and done, we will get meters per minute because the unitless units will, or the dimensionless units is what I should say, not unitless, but dimensionless units will disappear, okay? So dB by dt is going to be, all right, so I got about 14,576 meters per minute, which sounds like a lot, but to put that in context, that's about 14.576 kilometers per minute. Okay, which does make some sense if you think about, well, one, the light is doing a full rotation. I don't know what happened there. Okay, the lighthouse is doing a full rotation 4 times a minute, right? So, so that's about a full rotation every 15 seconds. Okay, so yeah, every 15 seconds we're getting a full rotation, and the beam of light is traveling over 500 miles, right? The shores are not 500 miles, but 500 meters away, okay? So that means the beam, right, is traveling fairly quickly across the shore in relation to the angular velocity, okay? All right, so there's that example. Let's move on to another one. All right, we'll move away from trig for this one, but let's say we have a steel cylinder that has a constant volume of 100 pi cubic inches and is being slowly crushed in a vise. All right, so we have the vise crushing down at a constant rate of 0.125 inches per minute. Let's find how fast the radius increases once the height reaches 4 inches. So what's happening here is we have this cylinder, right, that is made of steel, and it's being crushed in a vise, right? A vise is pushing downwards, and as it pushes downwards, okay, what ends up happening is the height of the cylinder starts going down, right? It's decreasing, but at the same time, the radius increases, right? Because the volume of the cylinder should stay the same. All we're doing is crushing the cylinder in a vise, right? So the height is decreasing as the radius increases. Okay? All right, so notice what I've done here. One, I've drawn a picture. Right? I always think that's a good idea. But as so essentially, and then I identified what things were changing over time, right? So when this is happening, the height is going down, but at the same time, the radius is moving out. So, okay, these things vary over time, so these are going to be my variables. Okay, but while this is happening, based on the scenario here, the volume is constant, right? The volume should be the same. So the volume here is 100 pi, and the volume here should also still be 100 pi, right, cubic inches. The volume of the cylinder is not changing. The amount of material, right, the amount of steel in the cylinder is still the same, even if it gets flattened all the way down to something like this, like a pancake. This would still have a very, very small height, okay, and a very, very large radius. Okay, so, but we would still have 100 pi cubic inches of material there. That vise isn't removing volume. Okay, so the volume is constant. So I always like to start here. 1 with a picture, 2 with identifying what is varying and what remains constant. Because then when I get a formula that relates all of these, then that tells me what I can put in as variables and what I can put in as constants. So the volume of a cylinder, right, is pi r squared h. So here's the formula that relates all of these quantities. Okay, but now, okay, I can put in the 100 pi because we have a constant volume for this problem. So for here, our constant volume means we can go ahead and plug it in. Now, keep in mind, we do not plug in the 4 inches yet. Don't plug that in yet. Remember, because the height varies. So we plug that in once we've differentiated. Okay, so now we'll differentiate. Okay, before we do that though, I think I'll cancel these pi's since we have pi's on both sides. So really we have 100 is equal to r squared h. Yes, I did that on purpose. And so now we can differentiate the derivative of 100. And I'm just going to write it out the long way real quick. The derivative of 100 is going to be 0. The derivative of r squared h, we're going to have to use the product rule. Okay, so derivative of 100, 0. Derivative of r squared h, well, product rule with chain rules because we're doing implicit differentiation. This is going to be 2r times dr dt, so this is the derivative of the first guy, times h, left alone, plus r squared times dh dt, the derivative of the second guy. Okay, so this we know. Okay, we were told what this was. This is a constant rate of change, and this is what we're trying to find, right? What were we asked to find? We were asked to find how fast the radius increases once the height reaches 4 inches. So how fast the radius increases, this is dr dt. Okay, so if we head back down, dr dt, this is what we're trying to find. Everything else we should be given, or it shouldn't take too long to figure out what we're trying to do. Right, so now we can plug in this 4 inches. Right, so this is what we are this is when we're freeze framing this situation to see what's happening when we hit a height of 4 inches. Okay. Now, how would we find the radius when the height is 4 inches? Well, we would go to our volume formula, right? So here we know h is going to be 4 inches. The natural question is, what is r? Well, we can get that from here. Sort of like how before we've used the Pythagorean theorem or other things to find any missing quantities. Here we are going to use this formula to find the missing quantity. 100 is going to equal r squared times 4, which is our h. Divide this through, we'll get 25 is equal to r squared, so r is equal to 5. Yes, it should be plus or minus, but since we're dealing with an application here, I know it has to be positive. All right, so r is 5 inches, h is 4 inches, and dh dt is, we were given that, let's see, 0.125 inches per minute. Okay, so since h is going down, it's negative 0.125 inches per minute. So here's a situation where the negative will matter because one of the quantities is decreasing while one of the other quantities is increasing. So we do need to introduce the negative there. Okay, so now we should have enough information to plug everything in here. Right, we have 0 on this side. We have 2 times r, which we found is 5 inches. Okay, dr dt, that's what we're trying to find. H is 4 inches. Okay, plus r squared, so that will be 25 square inches. Then dh dt is negative 0.125 inches per minute. And I'm totally honed in on that, so let me make that. Okay, so let's simplify this piece. And actually, let me go ahead and do the calculations here. Okay, so when you calculate these all together, we're going to get 0 is equal to 40 square inches times dr dt, this thing we're looking for, minus 3.125 cubic inches per minute. Now, the units should work out at the end because we're going to move this whole thing over to that side to get 3.125 cubic inches per minute is equal to 40 square inches dr dt. Now all we need to do is divide by the 40 square inches, and we should get the units that we're looking for because these square inches will cancel with two of them up here, and we're going to end up with just inches per minute, which is what we should get for dr dt. So dr dt is going to be right about 0.078 inches per minute. All right, so there we go. I'm not trying to belittle this. I'm not trying to imply that this is easy. Okay, I'm really not. However, the biggest piece of advice I can give for related rates is it's what some people call chunk, right? Chunk them, as in break it into chunks, where each particular chunk is a smaller manageable piece versus trying to think of the whole thing all at once. Because the first chunk, right? The first chunk is, well, okay, let me draw a picture to see if I can visualize what's going on. And then let me describe to myself what it is that's changing and what is that is not changing, right? What remains constant. Then I start with a formula that relates everything, right? Plug in my constants, let everything else stay a variable. Then we differentiate. Then we plug in what we have, find anything that we don't have, and solve for that final rate. Okay, so yes, I know that this is complicated. Okay, but remember to chunk the problems. Right? Chunking the problems is going to make things a lot smoother when you're trying to do this yourself. Right? Break it up into pieces. Just try and start with these with, okay, what is the first thing that I can actually do? Or I can draw a picture of what's going on. Then I can decide, okay, what things are changing over time and what things aren't. Okay? And so on and so forth. All right, so next up, let's say two boats leave a port at the same time. One travels west at 20 miles an hour, and the other travels south at 15 miles an hour, right? So the first question, after 30 minutes, how far is each boat from port? So if I wanted to draw a picture here, let's say the port is right here, and we're told that the first boat travels west at 20 miles an hour. So if it's traveling west, okay, at 20 miles per hour, then after 30 minutes, it should only get 10 miles, right? Because if it's going 20 miles per hour constantly, like at a constant rate, after half an hour, it should only be 10 miles, right? So the answer there is after 30 minutes, this boat's going to be 10 miles at the 30-minute mark. All right, then the other boat is traveling south, okay, at 15 miles per hour. All right, so in 30 minutes, right, in half the time, it should be, well, half of 15, which is going to be 7.5 miles. Okay, so now here's the question. At what rate is the distance between the boats changing 30 minutes after they leave port? Well, here's where the related rates part comes in. So I'm going to draw a bigger triangle here. Right, so our first boat is traveling at 20 miles per hour. And this in orange is its distance from port. Okay, the other boat is traveling south at 15 miles per hour. This in yellow is its distance from the port. The distance between the two boats is here. This diagonal, this is the distance between the two boats. Okay, so as these boats move further and further apart, the distance between them is going to be changing at a higher and higher rate. So even though that these are constant, as they move further and further apart, the rate at which the distance between them is changing is likely increasing. Okay, so let's figure this out. So all of these quantities are increasing in time. So we're not going to have any constants we can fill in, right? So I'm going to call this distance x, this distance y, and then this distance z. I'm not going to incorporate negatives here because all of these quantities are increasing, so we don't really have to worry about that. Okay, and then a formula that relates all these, well, this is of course a right triangle, so we can use the Pythagorean theorem. So z squared is equal to x squared plus y squared, and there is nothing to put in as a constant, right? So all three quantities vary, so we can go straight to differentiation. Okay, so we'll differentiate everything with respect to t. All right, so it will be the derivative with respect to t of z squared is equal to the derivative with respect to t of x squared plus the derivative with respect to t of y squared. Okay, and so we're going to get 2z dz dt is equal to 2x dx dt plus 2y dy dt. All right, and I'm going to start by basically canceling out all the 2's because, well, that's, the first thing we can do. So if z is equal, or z times dz dt is equal to x times dx dt plus y dy dt. Okay, now we are trying to find the rate that this green length is changing in. So that's what we're really looking for, is the dz dt. Now, even if you don't know that, what you're basically going to be doing is plugging in everything you can and solving for the missing quantity. All right, so we know that at this moment in time, because we're talking about in 30 minutes, right, the x is at 10 miles, y is at 7.5 miles, and we can find the length of z in 30 minutes using the Pythagorean theorem. All right, so kind of skipping a couple steps here, but it's going to be basically the square root of 10 squared plus 7.5 squared, which comes out to be right about 12.5 miles. Okay, so that should give us everything we need now to fill this all in. So we have the 12.5 miles, okay, times dz dt, that's what we're looking for. It's equal to x. Well, x was 10 miles. Okay. Then times its rate of change, which that was 20 miles per hour. Okay. Plus y, which is 7.5 miles, times its rate, which was 15 miles per hour. Okay, so notice these guys are coming out to be square miles per hour, but when we divide through the miles, it will get back down to miles per hour. Okay, so dz dt is equal to, okay, so all of this comes out to be 312.5 square miles per hour, all over, then we divide by that 12.5 miles. All right, so this mile cancels with one of those, and so we end up with, all right, so we ended up getting 25 miles per hour. Now here's something interesting, okay? What would happen if we, instead of going through all this work, just did Pythagorean theorem on the rates? Well, we get 20 miles per hour squared plus 15 miles per hour squared is equal to dz dt. So let's see if that comes out to be the same thing. So if we did, say, dz dt squared is equal to dx dt squared plus dy dt squared, okay, we'd get dz by dt is equal to the square root of, this would be 10 miles per hour squared. Sorry, no, 20 miles per hour squared plus 15 miles per hour squared, right, which would come out to be 25 miles per hour. All right, so it's interesting that it just ends up working that way, but if you think about it, we have the 20 miles per hour going this way and the 15 miles per hour going this way. Since it's all constant rates of change, it makes sense that we'll have the 25 miles per hour on the hypotenuse this way. Now, be real careful with this. This isn't always going to work for you. Okay, I would be hesitant to try it every single time, but it is fascinating to see that the Pythagorean theorem still holds when we have rates of change like this. Now, if the rates are variable in some way, right, then there's likely more work to do. But I found that to be an interesting property. All right, so to show you an example where this won't always work out that way, where you can't just apply the Pythagorean theorem to the rates, it has to do when all the rates aren't increasing, say, at a constant rate of change. So that's what we were looking at the last time. So this particular example, we're going to be looking at something where the sides of the triangle won't be moving along at constant rates of change. Okay, so here's the situation. We have a bug is moving along the right side of the parabola y equals x squared at a rate such that its distance from the origin is increasing at a rate of 1 centimeter per minute. Okay, so this is kind of difficult to decipher if you've never done a problem like this before. Okay, so we have the parabola y equals x squared, and we're basically just looking at the right side of it. So this side, here's y equals x squared, and we have a bug traveling along the parabola. Right, it's moving along the parabola, but it's doing so such that, in a way, notice what it says, that its distance from the origin is increasing at a rate of 1 centimeter per minute. Well, its distance from the origin is this line right here, which I'm going to call R. Okay, and this, we know, or we're told, is increasing at a rate of 1 centimeter per minute. So it's this length that is increasing at a constant rate of change. Now that's kind of difficult to show with some graphing software. However, what's happening is while that's going on, okay, at every point this is creating a right triangle, right, with an X and a Y. Okay, so for example, if we take a look at this graph I made here, we see that as the bug moves, it's creating this right triangle with the X and Y coordinates of the point. Okay, now it's doing so such that this rate is the one that's constant. These probably won't be, right? They're likely to be a variable rate of change. Okay, so let's see what questions we can answer about this situation. All right, so at what rate is the x-coordinate of the bug increasing when it reaches the point 2, 4? So specifically, we are looking at the point 2, 4. Okay, so we've got the parabola here, and we've got its distance, which we're calling r. Now that's the one that has the constant rate of change, but we want to know how this rate in x is moving once we hit this point 2, 4. Okay, so how we do that? Well, of course we're going to use relative rates, but notice there's not going to be any constants we put in, but we are using a right triangle. Okay, so we can use the Pythagorean theorem. Another thing we can do, okay, now we're only looking for the rate in terms of x. So since this point always comes from this parabola, every point along this parabola is going to be of the form x comma x squared, because that's what y is equal to. Okay, so y is equal to x squared. So we can actually write this triangle, in this case, as an x by x squared by r squared. Okay, so by the Pythagorean theorem, r squared is going to be equal to x squared plus x squared squared. All right, so this is one example where we can't just use the Pythagorean theorem of the rates because we have everything sort of moving at different weird rates here because, well, this formula basically reduces down to r squared is equal to x squared plus x to the fourth, or x squared times 1 plus x squared, if we want to do it that way. I think I'd rather leave it like this so I can use the power rule. But now we can go about differentiating this guy here. Okay, so when we differentiate with respect to with respect to t, excuse me, we're going to get 2r dr dt is equal to 2x dx dt plus 4x cubed dx dt. And so we can actually factor, well, first we can divide everything by 2. So let's start there. Divide everything by 2 to simplify. Okay, so, and we can factor out the dx dt. So we'll have r dr dt is equal to x plus 2x cubed times dx dt. All right, now we can start plugging things in. Well, do we know what all of our values are? Well, yes, we know that x is 2 in this situation. We know that dr dt is always 1 centimeter per minute, which means x is 2 centimeters. And we can find what r is using the Pythagorean theorem, right? If we're at the point 2, 4, r is going to be the square root of 2 squared plus 4 squared. All right, so this will be the square root of 4 plus 16, so that's going to be the square root of 20. All right, and we can factor a 4 out of that, so r will be 2 root 5. Okay. All right, so we have all the information we need, right? X is 2 centimeters, dr dt is 1 centimeter per minute, and r we found is 2 root 5 centimeters. All right, so that should be everything we need to plug in here to get 2 root 5 dr dt. Okay, so here we are. 2 root 5 times 1, that 1 centimeter per minute, is equal to 2 plus 2 times 2 cubed, all times dx dt. Now, you might be wondering, well, this is going to be centimeters cubed, right? Well, no, this x squared, that's, remember, just our y. Okay, so that's just still in centimeters, even though we're calling the value x squared. So it's really x squared centimeters. Okay, so no, I'm not really messing with the units too much here just because they're going to get extremely cluttered. And eventually, I actually stop writing all the units at every step once I get more of the hang of it and just sort of know what I need at the end. Okay, so, all right, so that's going to be 8 times 2, which is 16, plus 2, which is 18. So dx dt is going to be 2 times root 5 all over 18, right, which will be root 5 over 9, which is about 2.248 centimeters per minute. All right, I'm going to remember this value as we go along. All right, and there we go. Now, what's going to be a little more difficult is finding the answer to the next problem, which is now going to be asking about what's happening in terms of y. All right, so next up, we're going to ask at what rate is the y-coordinate increasing? So here, instead of just replacing y with x squared like we did before, we're going to leave y where it is until we get to the formula we're looking for. And this is still at the point 2, 4. Okay, so we're going to stick with this r squared is equal to x squared plus y squared, but in this case we're going to leave the y squared part alone, okay, and then go straight to the differentiation. All right, so it'll be 2r dr dt is equal to 2x dx dt plus 2y dy dt. So now this is what we're looking for. We are looking for the dy dt. Okay, and we should have, well, we have the x, we already found the dx dt, we have the dr dt, we have the r, all these things we've already found. So now it's just a matter of solving for the dy dt. Okay, so once again, I'm going to start by canceling out all of the 2's so that we get r dr dt is equal to x dx dt plus y dy dt. Okay, and now we can plug in all of these values. R we found before is 2 root 5. dr dt is 1. X we know is 2. dx dt we found in the previous step, okay, which is square root 5 over 9. Y we know is 4 since we're at the point 2, 4. And then dy dt is what we're trying to solve for. Okay, so once again, I have a bunch of 2's here, so I'm going to start by dividing everything by 2 to get rid of it. So I have square root 5 is equal to square root 5 over 9 plus 2 dy dt. Okay, so now we'll just move this over. So we have root 5 minus root 5 over 9 is equal to 2 dy by dt. Okay, now this, quickest way to do this would call this 9 root 5 over 9, so that this comes out to be 8 root 5 over 9, which is equal to 2 dy dt. And then we just divide by 2. Okay, to get at the end that dy dt is going to be 4 root 5 over 9. Okay, and this will be in centimeters per minute once again. All right, yes, this one, it was fairly abstract, okay, kind of complex, I understand that. However, if you can follow through this one, there probably shouldn't be any in the homework that really give you trouble. And speaking of, this should definitely be enough to get you rolling on the homework. Like everything in this class, there are way too many possibilities for me to go through every single one. However, hopefully this is enough to show how you tackle the problems, okay? Remember to always sort of chunk the problems. Break them down into individual pieces. Start with what is varying versus what is constant. Get that formula that relates all the quantities. Plug in the constants. Then differentiate. Leave anything that varies as variables when you differentiate. Then you start plugging things in. So don't really start plugging a bunch of stuff in for the varying quantities until after you differentiate. Okay? So I know it can be overwhelming to deal with related rates when you're first going through it, but just, again, take it a step at a time. And let me know if you have any questions. I'll see you on the next one. Cheers.